Tienes hasta las 7. Vale, y no te pases que tenemos un hangout.
¿Un hang qué? Lo que
Sí.
encuentro.
Buenas a todos. Vamos a tener la última charla justo antes de la entrega del premio.
So we start our last presentation before the award ceremony. Please stay for the awards. Okay, do not rush to the beer. Okay. So sponsors that help us make this possible: Fortinet, GTI, Finotech, PwC, Symantec, Tarlogic, Pay for Beer, Blue Indical Viva, which is a group of companies from BBVA, Capgemini, DXC, Everest, Kaspersky, Woodley, Deloitte, Security Center. All these three sponsor the White Rabbit Room, and the others sponsor the events in general. Those on top sponsor all the rooms, and these ones sponsor the security room. So thank you very much, Gerardo, for your patience. It is always a pleasure having you here. Okay, so he will tell you more about crypto Goofs. So I am Gerardo García Peña. I come from Pricewaterhouse, and today I will basically talk about cryptography. I will not go into Bitcoin or any specific uses of it. And the idea is to go into, but this is not going to be a boring lesson of EIX. I'm going to take a look at how these algorithms work, and I would like you to take away two powerful conceptual ideas so that when you face up a cryptography issue, you are in a position to face up to them, and so that you can get also an understanding about the problems, weaknesses, and how the algorithm works, so that we can make a decent use of it. Okay, let us go for it. Table of contents, introduction, 3 slides. Okay, let's go for it. I will go back so that you don't get distracted. So when we think about using cryptography, it's not a question about, well, I'm going to use cryptography now or later, but it is when we want to protect assets, with whom are we going to use it, and whether we will eat it up or not. In terms of when, it kind of sounds like a simple thing, but it is not that simple. Says that security is like a chain. It always breaks in the weakest parts. So when do we want to have that protection? It is very good to use all the cryptographic algorithms in the world, and then that will leave the information not encrypted in the database. So we want to use it whenever there is any interaction delivering information. So we need protection, we need encrypting. So often we find mixed models of work when we are protecting the channel, but we are not protecting the interaction of data. And then additionally, sometimes, well, all this comes from the revision or review of code. And I'm going to tell you why I decided to give this talk. I review lots of code, and sometimes I can see that we are trying to protect something, we make mistakes, or sometimes when we are creating new protocols, when we have a mixed use of cryptography. Okay, I said this is encrypted, this is this or that for whatever reason. So the mixed use would be very risky and very complex. And actually all the weaknesses that we've seen in TLS and SSL came from the release of plain negotiation. The first messages were exchanged, there were not all the content was encrypted, and then an encrypted channel had to be established, have to be created. But that's the ideal point, just to put a foot on the door and then to walk in. So this has told me that there are many implications to this partial encryption. So by the time we consider to introduce cryptography in our solutions, we have to take into account this type of small things. Obviously, we will not be indexing websites with HTTPS. So I want to give you examples of bad use, especially the mixed one. So this was atypical before. Oh, SSL consumes a lot. It's you have everything in Java. Yes, but it consumes a lot. Well, that's your problem. That's your problem. Everything is unsecure. Credentials are not secure, and the result and the experience is that we no longer trust anyone, and now we put everything under HTTPS. Actually, working with this hybrid mode forces you not to use HTTP solutions, and sometimes the service is published in both HTTP and HTTPS. So therefore, you can be a victim of HSL stripping, or someone may redirect a link with no encryption. You are exposing your cookies, your everything. And then going into more specifics, so we may find IIS 7.0 and 7.5. So some of these protocols were always through code 21, and that's where the negotiation of a start SSL starts. You start off in plain and you say, hello, I'm this server, and I want to start talking in start SSL. And then the negotiation TTLS starts, and then it ends up in encrypted communication. And then you could set a semicolon and then a list of commands that will be executed by the time the session will be encrypted. So skinny RTP. So many people have deployed the last generation phones and say everything is encrypted. Yes, but the old phones are not encrypted. But when an old phone talks to a new phone, it has to do a downgrade and goes into plain. And then my SQL, well, they were the winners, the big ones, and I say, okay, I start off with SSL. Oh, well, there is a package here that I just don't understand. Okay, well, forget about it. Well, the way to mitigate it at that time was to have certificates. But if they do not validate that you get the certificate, I say, okay, go for it, okay? So the name is background, I think it is. Okay, so the next question is who and what we want to work. What we want to protect, where it comes from, whom it goes to. Confidentiality, integrity, authenticity. So we are working on confidentiality and integrity, and I added authenticity. So that would be like, you keep it for yourself. So cryptography helps us protect these three objectives. However, we should sometimes understand that we mix algorithms with protocols. Algorithms help us build protocols, but they will not resolve our life. And when I say life, I mean ASA does a cryptographic summary, but they really make sense whenever you frame them under a set of strict rules where all the stakeholders and all the possible status are well determined. The best ones in cryptography, the ideal moments, the best moments is when you do a self-enforcing protocol. That means that no matter what you do, the protocol will force everything to work. These are the ideal protocols, however we cannot use them all the time, but it would be ideal. They have nothing to do with reg. Protocols establish rules. And that's a problem when you start cryptography, because you say, well, the packages, what's the shape of them? No rules. Okay, and then when you think about who and what, so it is very important that you take away this principle as a message. It will help you resolve many doubts. It is the Horton principle. It says authenticate what is being meant, not what is being said. Often we don't encrypt the context, the meaning, where are they, whom they go to, the time of the day, feasibility of them. And now I added that cartoon to say. Then, well, I will start talking about Alice and Bob. That's the only way to explain cryptography, just to create some, I don't know, expectations, okay, or some interest. Bob, well, we take for granted that Bob is the boyfriend and Charles is a man who is after Alice. A typical error here, well, in electronic banking, before and now, well, we have the customer, the front servers, and then the backend. So clients authenticate, sending the privileges or credentials. So we protect the channel up until front end, and then we do a forward of the credentials that have been received. And the question is, well, the first fire line, what is that? Well, the front end. And why the credentials? Well, I don't know. Well, because they make them more interesting. They can see the passwords of people. That is not necessary. We got it wrong. We just put the encryption layer in the wrong place. We will have to elevate it. We will have to lift it, where Alice is the client and Bob is the mainframe server. So if you get a front end, plain authentication without admitting that this is a mistake. And email, that's another example where many people say, well, email is encrypted through SSL, but that is seen by the email server and not the recipient. This is a basic concept that everyone understands, but it is confusing. So do you have database encryption? Yes, it is running under an IS system. Oh my God. TLS, SL2, this is the Horton principle poorly implemented. Taking account the advantage that SSL part of the message was not authenticated. Well, I've been here for 11 minutes and I still haven't told you anything interesting. Okay, where, how, where? So do not try to be creative. Do not be too creative unless you are sure of what you are doing. Cryptography is very complex. Minor, poor decisions are significantly amplified because data is unprotected. So the more you simplify it, the more positive it is for you. Simplifying it for you, meaning that you understand it, not only the attacker, because the attacker may be smarter than you. Therefore, so be aware that all the participants, including the plain text, the choice of a poor key, of a poor plain text, may disclose or may make you guess the keys that are being used. All the decisions have to be well thought of through performance parameters, security parameters, and we also want to assess and study all the weaknesses of the algorithm. This talk is intended to be kind of an exercise to help you understand exactly the work that we are doing. And then I tell you what to do for each algorithm. I will give you an example of IPsec. It's something that we all like a lot, it's wonderful, but from the viewpoint of cryptography, it's a disaster. It is highly complicated, it has very many modes of functioning. You may have the channel encrypted, but the message is not authenticated. Then you may do cut and paste, then you introduce authentication headers, everything breaks, then you end up like really crazy. If you go and tell me that IPsec is great, that's because you've never worked with it. So actually there is a paper published about how difficult IPsec is. Okay, now let us go into what is actually interesting. So random numbers. It is one of the most misleading things. It is not about good luck finding something random is very difficult, and you really need to be lucky for it. Random numbers are the basis of cryptography. All the work that we will do, sooner or later we will have random numbers. Often they are underestimated, and there are different type of random numbers are created. So we have the pseudo random numbers. These are often the ones that we work. These are like the nonsense numbers. There are a set of numbers that are, well, I'll tell you more about that. Well, the problem is that we cannot really show access, so that's why. So this will be quite random. This is an example that I wanted to share with you. So these random numbers are very slow to achieve. You don't expect them to be there. When you get them, you are surprised, and they are not as random as they look. And actually, to generate them, often you use sources from the physical world. PCs are deterministic and not good at generating random numbers, and you have to drink from many different sources. But some sources look random, and even from them, you can extract patterns, and sometimes they look like too random. That's negative.
Números aleatorios.
Whenever you need random numbers, try to keep things simple. That's really high, but anyway. Random is a source of random numbers, which is quite powerful, but it's very slow. Random numbers come from a source like this to generate with a hash algorithm without ever going to the end of that algorithm, producing numbers all the time. As we feed the seeds back into the source, we keep improving the randomness, if you know what I mean. And then random numbers are usually produced using different algorithms. These are the most important examples. Reviewing JavaScript, I saw this once. The CPU was bleeding, I can assure you. But sometimes you're in a hurry, you've been told that the hash random doesn't work, so I download this and execute it. And then these silly numbers. Here we have get time of day, load of the CPU. You're talking about aficionados. You're talking about those people that don't really know about cryptography, but specialists also make mistakes. In Debian, lots of random keys were deleted because after all the user base is rather limited, and then a study was published on public keys in the internet. And I'm talking about devices that can generate random numbers and yet are not able to generate properly solid keys. This has become green now. Here we can see this algorithm, which looks really nice. It's all over the internet. People used it a lot because it was invented by IBM. The bad thing is that when you do a 3D projection for this, you see all the planes for that function. Even Donald Luth said that this is one of the most malignant algorithms ever conceived for random numbers. If we took all the papers based on this algorithm and they were discarded, we would be talking about half of the papers that you would see published in the internet in the 80s and the 90s. Biases, a bad thing. When we have a function that returns something big, we apply something like this, and we are relatively comfortable. This is when you're trying to generate numbers within a range, or when you want to choose certain elements. If you apply this, if favor these digits at the expense of these other ones. Try to use an algorithm which is similar to this one. This discards any number which is above the threshold level. I'm moving very fast. These are algorithms of secret keys. We have blocks. Coding algorithms are usually based in blocks. We have GCM, which is currently the most fashionable one. And yet, this is a very good algorithm, but the hash is somehow weak. Its period is not too long. But even the algorithm that I'm using, that you may be using now, that could be very modern, very recent. You really need to pay attention to the way it operates. Never operate with blocks under 64 bytes. Take that into account. These are 4 typical operation modes for blocks. ECB is the first one. Using that one doesn't make any sense. You take one block, you code it. You take another block, you code it. CBC, which has become rather fashionable recently, many attacks are related to this mode. Here we are propagating the entropy from one block to another during a show on the plain text and coding. Then we have PCBC, which is really odd. So we make things complicated, so complicated that certain things cannot happen. Well, the result is PCBC, basically. And then OFB, which is really interesting. Because people go to Wikipedia, they say rubbish, rubbish, rubbish. This has to be the good one. I'm not saying it's the bad one, but you really need to pay attention to what you do with it. Certain repetitions using OFB imply that you're not using things, that you're not doing things properly. Block encryption this way leaves you unprotected. Where does this happen? In RC4. Here I have included this image. I tried to use another one, but I didn't like it. And they know what I mean. Since this has been coded, I thought I had the green light to do whatever I wanted. But anyway, when we get into this, bear in mind that in web or in OFV, repeating an EV is death. EVs, this is a common problem. People see there is a parameter, didn't have any idea, and they wonder, what is this EV about? I have nothing in my database anyway. This seems it has been hacked. The thing is, people use zeros everywhere. In CFB, we would see this. If this is all zeros, with plain text, this is what we get. We encrypt this for a text we know, and we see the outcome. After that, with X short, you solve the equation. You would see the flat file. In fact, this attack was targeting Office 2003. Is the pointer out of battery or what? In 2003, this is what happened. When recording the file, you would generate different versions. You could extract parts of the document without encryption. In Wi-Fi, we know about this. The beast attack is a little bit more complicated. It's easy to insert blocks using this. Rather than affecting SSL or CBC, or TLS SSL, it affects improper usage of CBC because you let the attacker use their own plain text, injecting an oracle that will allow the attacker to find out what was happening. Don't get into that because it's a big mess. It's a bad idea. Letting the attacker get control of flat text files. Okay, that's always a bad idea. You cannot always avoid that, but you have to make life as difficult as possible. So if we don't want to let the attacker control the flat text file, we also don't want them to have control of the key. We should wear a special suit when generating keys, believe me. Keys must be random and not generated by anything else than a machine. There are algorithms that have keys that are encrypted. You apply them and then you get the encryption. You arrive at the encryption. With some keys you have partial encryption as well. In Blowfish, you have something like this. Some keys can be inferred based on the encrypted text, and you should never apply any type of limitations to keys. Parity bits, moving to 56 bits, much easier to break into. So after talking about encryption in the symmetrical part, let me now talk about hash functions. This is something we use quite often and it's quite useful for us. This returns a number which is huge. In theory, it is impossible to find flat text coming from that figure, from that number. That gives you a cryptographic summary or a value which is unique for that text. It's like an ID, like a UID for that text. Obviously CRC is not a hash function. I've seen this in different projects. It is not a hash function. Hash functions by themselves don't generate signatures or anything like that. They generate a text identifier, a summary. A protocol must always be in place. They can be used in many different ways, like this one. This guy has encrypted everything using SH1. How do I decode it now? Well, you just laugh. Here we have the typical bad approach to hash algorithms. This is quite common. Password, hash. The hash for the password is what you see here. Well, rubbish again. Identical passwords have the same hash. And you can do pre-calculation of certain things, and so on and so forth. So whenever we encounter this, we recommend that you use specialized algorithms for the generation of hashes to store in databases. Let me crypt a script BDKF2. And if you insist in using hashes, it is highly advisable to do this, moving around everywhere. Another important question, what is the difference between MAC and hash? MAC means message authentication code. It introduces a key for authentication. A hash by itself can be calculated. A MAC forces you, if you know to get hold of someone that knows the key. It protects the messages. MAC algorithms are used to protect. But MAC functions are not an answer to any problem, okay? It is quite common to see that there is MAC applied to a message, but no MAC applied to the meaning of a message. When you work with MACs, with hashes, remember this. You need to decrypt the meaning, not the message. Otherwise, we will have repetitive attacks, you will have seizures, you will have convulsions, and you must never share the key used for MAC with the key used for encryption. because you're putting all of your eggs in the same basket, so to say, and that is not a good thing, believe me. Another bad approach for an algorithm? Well, the same goes for this air conditioning unit, CBC with a Mac. As I said, the problem is block injection with CBC. A fundamental principle with Mac is that they cannot inject, they cannot modify, they cannot alter. If you can inject blocks, bad news. And then CBC Mac is encrypting everything with CBC and leaving the last block aside as a verification code. When you use a Mac, you need to ensure that the algorithm takes those things into account. This is my friend Mac. This is a picture made by McDonald's. McDonald's and Coca-Cola. It feeds on Coca-Cola. And the next question is where we put the Mac. Some people say out of the encryption, applying Mac on the encryption. Some people say put Mac on the data and then encrypt everything. And some people go crazy and say take the flat text file and encrypt it and then do Mac on the flat text file. This is crazy. It doesn't do anything useful. It just gives you information on the text. I'm not sure it has anything positive, and this one has a benefit. When encrypting, when doing Mac on the encryption, in theory we will not be decrypting things that don't make any sense. So the flexibility of an algorithm, for an encryption algorithm, is something to take into account, and Mac gives us information on the contents. This means that we encrypt without thinking and we sign without encrypting, with all the corresponding consequences. And then there's the other possibility. Some people say that this is much better. Although this has the problem that this plain text can be forwarded. Here we don't have any information about the text or its MAC. The signature goes with the text without the encryption context, so whoever can encrypt can verify that this encryption was not important and the message is pure. And then we have an increase in the entropy of the message because it doesn't give any information about the contents. Obviously, if you don't encrypt the context, you can always do a forward. Public key algorithms, well, this is a mess. You probably have seen that you're downloading something which is completely legitimate from a dodgy website. You see a lot of buttons and you know that you are doing something wrong, very wrong. Well, this is public key cryptography. You have to choose wisely. Whenever you want to use an algorithm, understand its properties, understand the implications of using it, and understand its operation, its function. This is the best hammer for the cryptographer. RSA, for example, is useful to sign and to encrypt. And DSA, ECDSA is good to sign. And Diffie-Hellman is useful for an exchange of keys. People do all sorts of funny stuff, okay? So beware of that. Beware of the limitations of the algorithm you choose. Diffie-Hellman, the other day I was having a chat with a client that told me this was one of the safest algorithms. I said, this doesn't protect you against the man-in-the-middle attack. Negotiating with both sides. I'll probably get a gift at the end of the lecture. Never mind. Here we see Paddington that loves